All right, so now I'm going to talk about the Newton method. For root finding. Okay, and then previously we had talked about simple enclosure methods. So last time we discussed simple enclosure methods. So the first one was the bisection method. And the next one was the method of false position. Okay, and if you recall, these were guaranteed converge. If f is continuous on the interval from a to b, and the function changes sign. So f of a times f at b is less than 0. Okay, so that's one thing, but the problem is that these methods have a slow rate of convergence. So for example, with the bisection method, you basically get one binary digit of additional accuracy. It's like every time you iterate in general. Okay, so the question is, so let's look at an example of what I mean by slow convergence. So how many iterations does it take to find the root f of x, okay, on the unit interval to 10 to the minus 10. Okay. All right. So so if you recall, we had an estimate for the bisection method, which says that the nth iterate alpha n minus the root alpha is bounded from above by b minus a over 2 to the n. And we want this error to be bounded from above by 10 to the minus 10. Okay, so so we know b and a, b is 1, a is 0, so that's 1 over 2 to the n is less than equal to 10 to the minus 10. You can take the reciprocal of that, and that gives you 2 to the n is greater than equal to 10 to the 10. So that means that n is greater than equal to log base 2 of 10 to the 10, which is about 33.22. So n needs to be at least 34 in order to achieve an accuracy of 10 to the minus 10. Okay, so that's quite a number of iterations. So what other things do we need to observe? It's like about the simple enclosure methods. So the other thing is that it will fail if f of x has a root, but doesn't change sign. So obviously one example of such a situation is if f of x has a repeated root at a point, say x minus 1 squared, so there's a double root at 1, and that function doesn't change sign, but there is there's a repeated root at x equals to 1 here, right? And then the last thing, obviously, at least with bisection, is that you only use information about the sign of f of x. Okay, so the goal, as you might expect, is to construct a method which is better in some way, shape, or form. So we would like to develop a faster method okay, that uses more information than just the sign of f of x. Okay. All right, and this is going to lead to the first of many methods. It's like so the first method is the Newton method.